Hello, everyone. So, for today's episode of Frick Programming, we're actually going to go do challenges. Every Sunday from now on are going to be challenge videos. Gonna go on to the website Code Signal and pick out one of the pre-made challenges that they have, and we're going to go over it step by step. And we're also going to go over how to actually solve these programs. So, today we are going to do the rangeBitCount. I'll read it aloud. You are given two numbers, A and B, where A is greater than or equal to 0, but also less than or equal to B. Imagine you construct an array of all the integers from A to B inclusively. You need to count the number of ones in the binary representations of all the numbers in the array. For example, if A equals 2 and B equals 7, the output should be 11. And then they give you an example of how it comes out to be 11. I'll go over this example as well once we start putting into the solution of what we want to do. So let's go over to the handy dandy paint and let's go over this. So we have a starting point A equals, or really 5. So we have 0 less than or equal to A, less than or equal to B, and B is greater than or equal to A, but less than or equal to 9. And that's basically our constraints for this program. Sorry for my very piss poor handwriting. I am not used to writing on a computer, so it looks a bit off than my normal handwriting on pencil and paper. So this is our constraints for our program. So what we have to do is we have to, or the main part of the program is to return the number of ones in the bit representations. Now, the bit representation follows along like this. So I'm going to convert 1 through 9 into bit representation. So 1 is easily 1. 2 is 1, 0. 3 is 1, 1. 4 is 1, 0, 0. 5 is 1, 0, 1. 6 is 1, 1, 0. 7 is 1, 1, 1. 8 is 1, 0, 0, 0. And 9 is 1, 0, 0, 1. If you don't know how really to convert this, an easy way is to do long division with remainders. So let's take 3 into consideration. So I do 3, long divided by 2. So I get 1, I get 2, I get remainder 1. Now, so it goes into it once, and I have remainder 1. 2 can't go into this, so I remainder 1. Then you read it backwards like this, and it comes 1, 1. So let me do that again. I have 2, 9. 2 can go into 9, and I get 4, remainder 1. 2 can go into 2 twice. So I get 2, remainder 0. 2 can go into 2 once, and I get no remainder. 2 cannot go into 1, therefore I have remainder 1 go to 0. Read it back that way, and 9 base 2 equals 1, 0, 0, 1. That's how you were to solve it in binary. You can do this in tertiary, octo, and hexa, which are 3rd base, 8th base, and 16th base. Now, let's do this another way as well. So, if we just delete, well, I think we scrolled, yep, we scrolled all the way over. So, if I want to continue with this, and we want to do, let's say, that's 3, 4, that's 4, 5, 6. So let's do 6. So 2, 6. 6 divided by 2 is 3. I have no remainder. 3 divided by 2 is 1 with 1 remainder. 2 cannot go into 1, so I get 0 with 1 remainder. Read it backwards that way. 6 to the base 2 is 110. And that's how we were to solve it if you were to convert it through long division. There are other long division ways you can do this, but this is the basic simplified representation. To count binary, if you were to count, you would do 1 is 1. That equals 0. Carry the 1. Therefore, you have 2. If I just add 1, this equals 1, 1. I have 3. If I just add 1 again, and then I have 0 here, carry the 1. 1 plus 1 is 0. Carry the 1, I have 1. That's 4. And that's how you count in binary. But anyway, so what we need to do for this program is return the ones of bit representation. And the way we do this is we have to take from A to B. We need to 1, convert to binary, and then 2, count the ones, and then 3, return the count. That's how we're going to have to do this program. Now, there's many different ways that you can actually convert to binary, and then count the ones, and then return the count. I like to use the methods that come with Java. So you have a method called integer dot to binary string, which will take an integer, say integer x, and it will return a string representation of bits of x. Then what we could do is we can loop through string, then we get back. And we can check each individual char for the number 1. Again, sorry for my handwriting on here. I'm not the best with writing like this. For 1. So that's how we're going to do our program. So if I go over to our program and write this, what we're going to do is I'm going to make a loop. Well, first I need to set up a counter that I'm going to return. Currently, we're going to start the counter at 0. We're not going to have anything in there just yet. Then I have to make a loop for integer I equals a, because our starting point is a. I is less than or equal to b. B is our upper limit, and it's inclusive. We want to include it. We're going to increment I by 1 every single time. And then what we're going to do is we're going to make a string of bits equals integer dot to binary string of I, which is the current number that we're on. Then we're going to loop through the bits and int j equals 0. J is less than bits.length, which is the length of the bit string that we're going to get. And then we're just going to increment j by 1. Then we're going to see if bits.char at location j equal 1, the character 1, count plus plus. We're going to increment the count. So what this is doing is this method is going through the bit string at the character j, checking its equality to the character 1, And if it is 1, we will increment our count. And then what we're going to do is just return our count. Now, as you can see, the complexity of this is a minus b. Let's say that is our n. And then for each one, we also have to loop through its bit representation, which is another n. We don't know what it's going to be. Therefore, we have n times n. So we have n squared is our complexity of our code. This could be problematic if we were to run longer intervals. So if the distance from A to B were to increase tenfold, this would also increase tenfold or double tenfold in speed, which could be an issue. However, we're still hitting our 3 seconds of execution time, and since our constraints are really low, we don't really have to worry about that. That's something that you also want to think about when you're programming. Are my constraints low enough that I can make it complex, but not too complex where I go over my execution time limit? Or is my constraint such a large thing that I can't make this complex? I have to make it as least complex as I possibly can so that I can run an execution time. I ran sample tests and we passed all 5. If we passed all 5, I might as well just submit to see if I can get it right. And I got it right. So that's how we do this challenge of rangeBitCount. Thank you very much for watching, and we'll see you guys next time as we go more in depth on the Java language. Thank you very much.